So y is defined as log x base a if and only if you can write in exponential form that x is equal to a to the power y. Now, there are some restrictions here that surround this definition. The first restriction to note is that, number one, we want a to be always positive. The base should always be positive. In fact, you may have learned this through the exponential function in grade 10 and 11, that the base is never negative. Now, I know someone is thinking there, but hang on a second. We've had f of x is equal to minus 2 to the power of x. Well, that negative does not apply to the 2. This negative actually applies to the invisible 1 in front of the 2. Remember, in general, the exponential form has the form, the exponential function has the form. I think I must try to slow down. The exponential function has the form k times a to the x. Remember that, right? So the base is never negative. Even in exponents, we never had a negative base. So it's very important. We're gonna be deliberate about this because it's an error that is often made when it comes to logs. So one very important to note is that we want a to be always positive, but not only that, we want a to be different from 1. And this is for obvious reasons, because if a is equal to 1 here, for example, and I'm reasoning with the exponential one because we already know this. If a is equal to 1, then imagine you're going to have x equals to 1 to the y. Now, irrespective of what the value of y is, this thing will always be the line x equals to 1, which is actually a vertical line. So it's a problem because a vertical line is not an exponential curve in its nature. So we want to have an exponential curve. And if we're going to have an exponential curve, a must be different from 1. Another important thing that I must then warn you about is that we actually also want x to be a positive number. Now I'm talking in the context of the logarithm, of course, actually, which also will apply to the exponential in this case, by the way. So check this. We want x, very, very key to note. And your calculator is actually well aware of this. If you try and press a log of a negative number, the calculator will tell you, I don't know what you're talking about. So, by the way, it can be any real number as long as it is positive. On the other hand, the value of y in the can be really any number. It can be positive, it can be negative. We will accept that. Okay, so it is very key that you note these restrictions. They will help you to understand why some things happen as we go along our journey of logs, especially when we get to inverse functions. Now, there are some few rules that we always come across or we always have to use when dealing with logarithms. Okay, there are some rules that we need to be aware of, and I'm going to share these rules. However, I will not really share all of them. I will share rules that I know are within the scope of the curriculum. In other words, rules that you are likely to experience. So very, very important. I'll share that. One of those key rules, so because these are not rules, I'll just say some rules. So just as we have laws of exponents, if you can think of laws of exponents, so we also have laws of logarithms or logarithm. It's after 4, so my English is gone. Logarithmic laws. Okay, so we also have that, or laws of logs, whichever way you want to phrase it. Bottom line is these are rules. Okay, now one of the rules, as I said, I'm not going to list all of them because some of them you don't really need them unless you're doing further studies. One of those laws is this one, and this is the popular one, which you're going to use as of today when we talk about the geometric sequence or even the series. One of them is that if I have a log, all right, of a number x, and this x is raised to some number k, of course, we have base a here. Then what I can actually do is I can write this as k log x base a. Can write it like that. Of course, here we must also note that k can be any real number. Guys, real numbers are made up of what? Rational numbers and irrational numbers. Irrational numbers are those weird numbers like pi, square root 2, you know, the square root of any number which is not a perfect square, basically. Those are irrational numbers, right? And then we also have rational numbers, which are what? Fractions. But then fractions are made up of integers. Okay, integers are an extension of whole numbers. And whole numbers, natural numbers, the only difference in our South African context is the number 0. So in other words, a natural number is a whole number is an integer is a rational number. Okay, so don't be intimidated by whatever is in the exponent there. When we say k is a real number, we mean it can literally be anything. You can have anything in the exponent. It could be a fraction, it could be a decimal, whatever it is, just treat it as a number. Treat it out of principle that when we've got a number in the exponent and we are dealing with logs, this is what can be done. So I need you to note this. And of course, this goes both ways. So from left to right and right to left, it goes both ways. It does not only apply from left to right. And I have said this again in the previous lesson to say that's the thing about mathematics. We will not expect you to know things only from left to right, but we will also expect you to know stuff right to left. So this law is very important. I know you're going to come across it and you will need it in your high school career well and within the scope of your curriculum. Another one which I need you to be well aware of is what they refer to as the change of base. And what literally happens here, you are in a situation where you have log x base a and you are dividing this by log y base a. What is interesting to note here is the fact that you've got the same basis in each case. So we are saying if this is the case, then you can actually rewrite this as log x base y. And I want you to actually try this out in your calculator. In fact, you can go test all of these out on your calculator. And for example, just take log 5 base 2 and divide it by log 3 base 2 and see if that really gives you the same thing as log 5 base 3. Okay, that should work. Otherwise, I'll have to resign as a maths teacher with immediate effect. All right, cool. Now, number 3, the other one that I needed to note, and this one I must say, particularly for functions, we've had papers in the past, we've had those kind of situations where this law actually was quite useful. So I need you to be well on board when it comes to this law, because you know what? It will be useful later on. This one may not really be useful when it comes to the geometric sequence or series, but I can assure you when it comes to functions and their inverses, this will be extremely useful. And here it goes. This is what it says. So if I've got a log, and I want you to see where it comes from. If I've got a log of a fraction, basically my log number is a fraction, and I still have base a. Watch this. Remember, the fraction 1 over x can actually be written as x to the negative 1. So that's base a, right? Remember, it can be written as that. Now, watch what's going to happen here. I'm going to apply law number 2. Law number 2 basically says you've got an exponent, then just make that exponent the coefficient of your log. So that's what I'm going to do here. I'm going to write this -1 right in front of my log, but I'll make it an invisible 1. So I'm just going to go negative and I'll go log x base a. That's it. So this actually comes from this first law that I started with. Okay, so beware of that. Be aware of that. But not only that, there's an interesting one. And I'm so sorry, I do not have the luxury of time to show you this one. But when we do inverse functions, you will actually get to see how it happens or how it comes about. But I can actually, if I don't want to have this negative in front, I can actually do this. This can be written as log x base 1 over a. And I know this is the part that's going to shock you for now, but I'm telling you, I promise you, I keep my promises at least here. I promise you when we do inverse functions, I will show you. If I do not, may someone in this room remind me and say you said you're going to show us that law 3 of logs, where it comes from. So this part is really the fun one, and I'll show you that with comparison to the exponents. Okay, so two important ones, or maybe for now, the one that is, yeah, two important rules for now is 1 and 2. The second law, I'm sharing this one because it also becomes handy when you do financial mathematics and you're doing the compound interest kind of thing, and you have to solve for n in the compound interest formula. So this one has also become very useful. So as you can see, concepts are really integrated. You not only gonna use logs in geometric sequences or series, you're gonna also need this for your financial math. You're also gonna need this for your functions and inverses. So, and again, you can even use this in your algebra, really, when solving some exponential equations. If you feel like going logs, I don't think that's outside the scope of your curriculum. You are more than welcome to use these also in your exponential equations, right? So that's that. Now, there are some notes or some statements that we need to be aware of, that we must be fully aware of when it comes to this. And I want to fix those, or rather write those down, so that when I move on, or as I move on, we are fully aware of these. Okay, so very important things to take note of, and I'm going to share that with you shortly. I just need to change the battery of my pen here so that I'm able to keep writing. Otherwise, yeah, this lesson will not go on. Okay, I have it. Just a second, please. Okay, we are back. The pen is now fine. The battery is replaced. Okay, so what are those important notes or principles to note? So please note, and again, you will see and appreciate this very well when we do inverse functions. Please take note that if you have the log of the same number and the same base, you will get 1. And maybe we should explain this in the context of the definition. Remember, our definition says y is equal to log x base a if and only if what? If x is equal to a to the y. Remember, that's what it says. Now, I want you to think of this, right? If I've got log x base x, so think of this now. This is basically x as well, right? That's what I'm saying. That's what we are saying. Then we've got x is equal to x to the y, something of that nature, right? Because we're replacing a with x. Now, obviously, this is true if what? If we take note of the fact that there is an invisible 1 there. Okay, that's what it means. So y must be 1. Hence we've got this here. So log x base x is equal to 1. That is very key to note. Another important one, the second important note, is that if I've got log 1 base a, I will get a 0. Okay? Again, this has to make sense in the context of the exponential, because we know in the exponential, anything to the power 0 is 1. You see that? That is quite important, all right? Few things that you need to be aware of also is that in as much as like I said, that we don't want the negative exponent for the base. In fact, we also don't want the 0 exponent for the base. Look at this. Let's go back to the definition here. I said a must be strictly greater than 0 and a must be different from 1. So that is another way of saying a cannot be 0 and a cannot be negative. So please beware of the following, that in the context of logs, log x base 1 has no meaning. It means nothing. So which means it's sort of undefined. We don't know what it is. Furthermore, a log of a negative base does not exist as well. So similarly, log x base a also has no meaning, where a is less than or equals to 0. In other words, if a is negative or a is equal to 0, there's no meaning to that. Another nice thing that I thought you should be aware of is that if I just write log x, you must know that we assume base 10. There is actually a base 10 that is there, but we do not write it. So when the base is 10, we don't write that base. Okay, it's assumed. So it's sort of invisible. So please beware of this. It is also quite a key component of your curriculum, which you need to be aware of. Okay, other nice to haves. Again, these ones are not really important, but they're very quite cool rules, which if you think about all the rules that are, or few rules that I've shared, you will see why they make sense. If I have log a to the x base a, this is actually the same as x. Another one, if I have a base raised to a log, watch this one, a to the log x base a, this is actually x. So that's another a nice one to take note of. All right, this is just for fun, for your enrichment, by the way, or just in case it comes through. So these are the key things that we need to know about logarithms. And if you like, you may maybe want to take a screenshot, especially of this one, because you're going to need this as we start with the geometric sequence. Okay, so hopefully you've noted all that, because you will need this when we do some examples. So without further ado, let's talk about the geometric sequence. Let's talk about the geometric sequence. And again, I'm kind of starting with the definition here by explaining or defining what makes up a geometric sequence, okay? We say a sequence is geometric if the following is true. If the ratio between consecutive terms is constant. So what does that mean? If I have a geometric series where I've got the first term, the second term, the third term, and so on. If I've got a series like this, then I can conclude that this sequence is geometric if the following is true. If term number 2 divided by term number 1 gives me the same value, the same number, be it fraction or decimal or whatever, as long as it's a real number, if it gives me the same as term number 3 divided by term number 2. And we will refer to these as our constant ratio. So when the examiner tells you, here is a geometric sequence, then this is what you must expect. Or they say, here is a geometric series. This is what you must expect. Please take note of this. Just as we did with the arithmetic, remember the arithmetic sequence has its own signature, has its own trait, has a way it looks like, has its characteristics. So it is with the quadratic. We know in the quadratic, the second difference is constant. We also then are noting today that with the geometric sequence, we have a constant ratio. Okay, remember the word ratio implies division. Okay, so when you divide term 2 by term 1, you must get the same answer when dividing term 3 by term 2, and that's what we will call our constant ratio. The general term, we do not have time to derive this one, so I will write it down for you. The general term, known as Tn, is usually given as a times r to the n minus 1. Again, just like the arithmetic sequence, a here is your first term. And if you are in doubt, I can quickly show you that if I calculate term 1 and I substitute 1 in this general term, I will actually get a, because anything to the 0 is 1. So as you can see, out of principle, once again, term 1 is always equal to a in a geometric. All right. And of course, we know that R here is the constant ratio. Okay, which you know how to calculate, or at least you are given a way of calculating it. All right. Now, of course, this is all talk and talk and talk, and sometimes they say talk is cheap. So let us give you an exhibition of how all this comes into play. And I'll take this question here to illustrate this. We are told to consider the geometric sequence 3, 6, 12, and so on up to 1536 or 1536. There is something that I mentioned when we spoke about the linear or arithmetic sequence. I said whenever a last term is given, you must know that you can equate that last term to the general term. So please, whenever you look at a sequence, or even if it's a series, and you realize that, oh, the last term is actually given, you must know this principle that that last term is equivalent to the general term. And we use that to actually help us find the total number of terms in the sequence. Now, how do we find the general term? Well, first of all, we know that the general term of a geometric sequence looks like this: a times r to the power of n minus 1. And we know that a is the first term, so We have 3 times r to the n minus 1. We don't know what r is, but we know how to find r. So r should be 6 over 3, which is what? A 2. And indeed, if I do 12 divided by 6, I get a 2. So this is just for me to double check. But of course, if you trust your first approach, then that is good. And I guess you really don't need to double check in this case again, because they have already told you it is geometric. So this must be of a truth. Therefore, to close off question 1, the general term is as follows. It is 3 times. Now, I usually say, okay, sometimes brackets is not a big deal, but if you know you're going to make a mistake, and maybe if you know that the way you write the dot is very small such that you yourself cannot see the dot at times. If you know that is the case, then please, then you rather be safe than sorry, then please use brackets. Then use brackets, because at least brackets you will be able to see. So beware of that, please. You don't want to lose marks unnecessarily. So these two are actually one and the same. Okay, just want to make it clear that please take note that it is not 3 times 2, which is 6. No, it is 3 times then 2 to the n minus 1. As again, mathematics is a language, so notation is very important. How we write things, how we express things is very key. Now, we want the value of the 6th term, or term number 6. So we just substitute in the general term here. T6 will be 3 times 2 to the 6 minus 1. I know the DBE makes this one a big deal, so make sure that you actually show the substitution. Once you have done that, you don't have to worry about the middle step. You can just plug and play in your calculator, and my calculator here gives me 96. So term number 6 is 96. We do see students writing TN instead of T6. And I've seen the penalty being given there. So if you're going to write Tn is equal to 96, I promise you that does not make sense, because when you say Tn, you are saying the general term. Now you are saying that the general term is 96, it's constant. Sorry, that does not make mathematical sense. So you will be penalized in that. If your teacher does not penalize you, unfortunately, the person who marks your final exam might penalize you, depending maybe on their mood. I don't know. Right. So that is the second thing there, that you need to be meticulous in your writing. Number 3, which term in the sequence is equal to 384? This means that I have a term which is 384, but I need to find the position. So I'm going to solve for n. Now, the principle that you're going to use here is that of exponential equations, or your prior knowledge that is being invoked here is that of exponential equations. You need to know what's going on in exponential equations, okay? So what we do here, we usually divide. We want to divide by 3. So I'll write that down. It's not necessary, but I will write it for someone who needs to remember what happened here. So I'm dividing this by 3, and I get a 128. Which is 2 to the n minus 1. Now, at this stage, I know you're going to get your calculator, and you're going to go 128, and then you say equal to, then you say shift fact, and then you get 2 to the power 7, right? That's fine. 2 to the power 7 is equal to 2 to the n minus 1. Now, since the bases are the same, surely the exponents must also be the same. So surely 7 is equal to n minus 1. And for this equation to be true, n must actually be 8, which means that term number 8 is equal to 384. You can write it nicely, then say, well, T8 is 384. Now, sometimes you don't always have a nice number like 384. And I want to show you how logs come into play. I want to show you how you could have used logs or one of the log rules to sort this mess out. So let's say you don't know the shift fact trick, or you find it to be a waste of time. Then what you could do is, by applying law number 1 of logs, you would go, well, log 128 is equal to log 2 to the power of n minus 1. And then n minus 1 is your exponent. So you are allowed to bring this down and say log 2, log 128. And what does this mean? You can divide by log 2 both sides. So you have log 128 over log 2 is equal to n minus 1. Again, I must indicate that this step here is not really necessary. You could move literally from that one to this one here. And then once you are there, you could write this, and then you get your final answer, where you're going to say, well, you can press in your calculator, right? I hope you know the log button. So here it is. So you can start off by saying, well, log 128 divided by log what? Is it log 12 or 2? Oh, it's log 2. Divided by log 2, and then we get our 7. So the calculator will understand your language. So you have 7 is equal to n minus 1, and then you know what to do from here. As I'm saying, this is in a case where you do not have a nice number that can be prime factorized, or that can be written in terms of the base that is on the right-hand side or either side of your equation. This is how you will then apply logs. It could be when dealing with the geometric sequence, or when dealing with your financial maths. You want to find the unknown n value in the compound interest formula. All right. And then the last one, number 4, how many terms are there in this sequence? This is where we're going to use the fact that the last term is equivalent to the general term. So we're going to take this 1,536. And so we know Tn is equal to L. Therefore, what is our Tn? Tn, remember, is our general term. So 3 times 2 to the n minus 1 is equal to our last term, which is 1536. And again, we're going to try out here and divide by 3. So 1536 divided by 3, and I get here 512. And I think 512 can be written in terms of base 2. So again, you are more than welcome to try out logs there. So I have 2 to the n minus 1 is equal to 2 to the 9, which means that n is equal to 10. Again, I don't know how pedantic the examiner or the marker is going to be, so you may want to write all steps. It's always safe, because then you will have no regrets when you do that. So that is how you will answer question number 4, this one here, that required you to find the number of terms in the sequence. Of course, just as we saw with the quadratic number pattern and the linear number pattern, we may be asked, even in the geometric, to solve for x. Now, we are told that x minus 5, 2x minus 4, as well as 6x are the first 3 terms of what? A geometric sequence. We must find the possible values of x. What do we know? We know that in a geometric sequence, there is a constant ratio. And this is what it means to have a constant ratio. Guess what? X minus 5 is my first term, 2x minus 4 is my second term, and 6x is my third term. So if I do a simple basic substitution here, I will have 2x minus 4 divided by x minus 5 equal to 6x over a 2x minus 4. And then some say it is indeed joyous to be an Orlando Pirates fan. So there we go. the bones, and then we're going to multiply 2x minus 4 by 2x minus 4, and then we're going to multiply 6x by x minus 5. Now the left-hand side is your basic FOIL. That is 4x squared. Please be careful there. 4x squared minus 8x minus 8x is minus 16x, and I'll have a plus 16, and then this will become 6x squared minus a 30x. It does not matter whether you had 6x into x minus 5 this side and then this product this side. It doesn't really matter. You would still get the same thing, okay, the same result. This is just a basic quadratic equation, and we, by now at grade 12 level, we know how to solve quadratic equations. So I'm going to work on the right hand side and have my equation in standard form here. So then 6x squared minus 4x squared is 2x squared. You see, I have the liberty of doing this. It may not cost me. But if you know that for you, you actually need to write every single step. If you know that's you, please be good to yourself and write those little steps. Do not undermine them. Be kind and gentle to yourself and actually write them down. So 6x squared minus 5x squared, that's 2x squared, right? Then I have minus 30 plus 16. Be careful there. Be careful there. And hence I said what I said earlier on. So I'm going to have a minus 14x here. And then finally, I'm going to have a minus 16. But then I notice, oh, 2 is a highest common factor. So this is x squared minus 7x minus 8. Then I'll just have fun here. Factorize this x, there's got to be a minus 8. And this here must be a plus 1. And therefore, x is equal to 8, or x is equal to minus 1. And this is why the instruction said determine the possible values of x, because you can get more than one value. So please don't be hasty here and say, oh, the negative value is invalid, so it must be rejected. No, you will lose a mark. Look at the instruction. It said possible values, s in brackets, which suggested that you could get more than one value. And so you must be okay with this. You got two values. That is fine. If I had put a restriction maybe and said where x is a positive integer like that, then you will reject the negative 1. Or if I said where x is a negative integer like that, then you would have rejected the positive 8 and gotten a negative 1. Or if I said where x is positive like that. You see, all these are synonyms. Okay, so please, when you look at your textbooks, don't skip these symbols. If you don't understand what a symbol says and all that, interrogate, ask, find out what it means. You're more than welcome to ask me as well at any time. I will do my best to answer you. So please don't take these symbols for granted and ignore them. I think personally that's one of the things I did in high school. I just ignored what symbols meant. Although I got lucky with an A, but I promise you, I would have probably done way, way better if I paid attention to what the symbols meant and so forth. So please, guys, pay attention to the symbols. I try my best to explain what they mean. Now, here's a nice, interesting question. We've got here a geometric sequence and an arithmetic sequence, and we have to solve for x and y. If you think of your question 1 in grade 12, your question 1 is typically a solve for x, then it is followed by a simultaneous equation type of question where you have to solve simultaneously. Here, it is not asked explicitly to say solve simultaneously for x and y, but that's a prior knowledge that you may also need to use in this instance. Now, let us see what we can come up with here by using the principles of a geometric and an arithmetic sequence. Looking at my geometric sequence, I now know that y over x has to give me the same value as 8 over y because that's my constant ratio, right? When it comes to the arithmetic, I deal with what we call a constant difference, which means, let me remind you, so in the geometric, we deal with a constant ratio where T2 divided by T1 is equal to T3 divided by T2. With the arithmetic, we are dealing with a constant difference where D is equal to T2 minus T1, and this must give me the exact same value as T3 minus T2. So what's going to happen here, I'm going to go x plus 1 minus a 1. So here I don't really use brackets because 1 is a constant term, but watch what happens on the right-hand side. I will go y plus 1 minus, use brackets because x plus 1 is more than 1 term. It's a binomial. In fact, so use brackets, please. I told you, you know there's a catch there. So now I'll go y plus 1 minus x minus 1. You see the importance of brackets. You wouldn't have seen that if you didn't have brackets. And the left-hand side is just an x because 1 minus 1 is 0. But again, you still have a 1 minus 1 situation on the right-hand side. So you're actually left with y minus x on the right and then x on the left. And finally, 2x is equal to y. Then when you get to this blue equation, if we cross multiply here, we're going to have the following. We're going to have 8x is equal to y squared. Whenever you have exactly one fraction on the left and one fraction on the right, you can always choose Orlando Pirates. You're going to come right there. Okay, then, so we have 8x is equal to y squared. So please take note, oh guys, I beg you, right? Please take note that this is not 2y. Sometimes I have students doing this cross multiply and they write 2y instead of y squared. So that's very dangerous. Be aware of this. Okay, now we're going to use substitution, right? I know that y is equal to 2x. So in the place of y, I can actually write what? A 2x. So 8x is equal to, and I'll write the 2x. You see, brackets will always save you. And I said to you, I'll always preach this. Make it a habit to use brackets whenever you substitute. So that's what I've got there. And then now we're going to work this out. This is 8x is equal to, watch this now. Oops, what happened there? So please take note. It's going to be 4x squared because you are squaring the 2, you are also squaring the x. Let me remind you, 2x all squared means 2 squared and x squared. And so the 4 comes from squaring the 2. Please beware of that. Then what I will do here, I notice that 4 can go into 4 and can go into 8 as well. I'll write this as 4x is equal to x squared. Now, most students will often do this. Will often say, but I can also divide by x. That's what students will do. And then when they do that, then they'll say, oh yeah, I know what x is. X is equal to 4. Now, what have you done in this? Of course, you're going to say there's nothing wrong. And I'll tell you, well, you're not going to get full marks. What is wrong with this? You have changed the meaning of the equation. Your equation in this line was a quadratic equation. It's an equation that said to you, you are anticipating 2 solutions. Now you are dividing by x, and what happens? You are throwing away a solution. And so you end up with only 1 solution instead of 2 solutions. When the question also said to you, determine the values of x and y, suggesting that you could have more than one value for x. So please don't do that. Whenever you have a quadratic, no, fundamental principle of algebra, right? You must anticipate 2 solutions. So how do I get my 2 solutions here? Well, a quadratic equation must be written in standard form. And that means the one side of the equation must be 0. And then everything else will be on the other side. And now I can factorize, and I'll do this by using the highest common factor method. But still, if you thought you felt like using the quadratic formula, which was going to take forever, that's still fine. For me, I'm interested in you getting full marks. So we now know x is equal to 0, or x minus 4 is 0, which means x equals to 4. So there are your two solutions. Then I'll substitute there. So I know then y is 2x, so y is 2 times 0, which is 0, or y is 2 times 4, and this gives me an 8. So I know when x is 0, y will also be 0. And then when x is equal to 4, what will happen? Y will be an 8. So very key to take note of that. Gwandumisa, if you cannot see the screen, try and please manage your Zoom settings. Just check there if you have actually managed that. If it means logging out and then logging in again, please try that. Otherwise, what I'll do, I will stop sharing and then I will reshare my screen again, maybe to try and solve your problem. Yeah, I'm hoping this also helps to solve your problem. So this is the idea, guys. This is what we needed to get to. All right. I think what I'm gonna do, seeing that we have already hit the 1 hour mark, what I'm gonna do is I will rather give you a homework question to try out, and this is just to make sure that you are on the same path. I do not lose you. I don't like, just covering content for the sake of covering content or the curriculum. I often prefer to actually see whether you are on board or not. So what I'm going to do, I'm going to grab a question from that booklet of ours. If you remember the past paper booklet that I shared in the group chat. If you don't have it yet, I will resend it so that everyone has access to it. And someone, please, if you are affected by this and you're hearing me, do send a direct WhatsApp if I have not sent that booklet within the first 5 minutes of having completed this lesson. Okay, please do that. All right, now, what do I want to do? I want to do this. Okay, so I'm going to resume the sharing. Again, you should see my screen. I hope you still remember, by the way, your sigma notation. We did a bit of that. So there's a nice question, 3.3. Right. So I will want you to do this. I'm just going to make it basic before we become sophisticated. I'm just going to make this task basic. So I will want you to do this. I'm going to put it on display now. You see, very nice, simple problem. Just to make sure that you are all on board and you need to remember what we did as far as logs are concerned. Another one is this one. I want you to do this one as well. So I'll just give you two problems. Not a lot. Two should be fine. Okay. So if you will, guys, please, let's just save time here as well. Please also do this one, just this part. Forget about this. We will get there, and forget about this. We will get there. So basically, I want you to just do these two problems, 6 marks. So try and finish this within 6 minutes. If you can do that within 6 minutes, that's a very good work rate. It means you know what you're doing. If you cannot, don't be hard on yourself. We're going to practice, 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 and we will eventually get to master this. All right. So that's about it. Let's stay tuned in the WhatsApp group. I will keep sending updates as to when our next lesson is going to be, and I'll share the booklet and so forth. So cheers, guys. Thanks for tuning in. We will meet then in our next session. Okay, cheers.